The purpose of this video today is for us to get a better feel for what a derivative is, and we're going to use some slides we've had from other parts of this unit and sort of bring it all together into one, hopefully into one concept so that we can really understand what a derivative means. This was a slide from earlier in the semester where we took a picture and actually drew in a slope of the tangent line at the point x equals 3. And so you'll notice we drew in that red tangent line. And then in the next picture, we actually drew the triangle so that we could count rise over run, because derivative is slope at that point, slope of the tangent line at that point. And if we count, we can see that the rise is 3 and the run is 2, and it's because it's a -2, then our slope is -3/2. The next gives us a feel for what that means in terms of a table. So if we look at the table, we see that as we get closer to 2 and calculate the average rate of change between the 2 points, 0 and 2, 0.5 and 2, all the way up to 1.9999 at 2, then think about that as being the secant lines getting closer together, the points getting closer together, so that the secant line, and you get the slope of that tangent line, which here would be 19.6 meters per second. So it gets across the idea that it's an instantaneous velocity and an instantaneous rate of change. So far we've talked about slope of the tangent line, instantaneous velocity, instantaneous rate of change. These are all the notations that you might see for, or most of them that you might see for the derivative. So the one we use the most often, of course, is the f prime of x and y prime, but you might see dy dx just as often. The rest of them probably less often, but we wanted to make sure you'd had a chance to see those and recognize them as being the notation for derivative. This link that will be active when you go into the PowerPoint through Blackboard, you'll be able to go into a picture that we used in class, or one similar to the one we used in class, where we came up with this definition of derivative by saying if we had the point x and it was another point that was a distance h away, we called that point x plus h. And we found the slope between them and then wrote that into this formula with the limit definition of a derivative. So I wanted to remind you that this is the way right now that we are finding a derivative if we're not drawing a line on a graph. We're looking at the definition of the derivative, the limit definition, which helps us find what a derivative is. We did one example of that using x squared. So I wanted you to be understanding what we had found when we found that derivative. So we had the function f of x equals x squared. We used that limit definition from the last slide and found out that the derivative, f prime of x, was 2x. Now that means that according to what we're looking at for the derivative is that 2x, function 2x, will help us find the slope of the tangent line or the instantaneous rate of change of any point x on that function. So let me show you what that means on a graph, and then we'll talk about what it means if you actually calculate. So I had done this graph on a grid. Now the only thing I don't like about this grid is that the x hash marks are 0.25 to get between the 0 and the 1, and you can see that you have mostly 5 hash marks between the 0 and the 2. But it looks like it might be a little bit more than that, so it's a little hard to count, but at least it'll give us a general feel for what we want to look at for this slope at a point. So let's look at the slope at 1. I'm going to draw in the slope of this tangent line at 1. If we were to count those hash marks in those grids, you can see that I've gone about 2, going from 0 to 2 here. And this is about a distance of 1 if we count the hash marks. So we just found out the slope at 1 is 2. Notice that that is the value of the derivative. We found the slope at 2, at 1, and at 1, that's what that value is. Notice what will happen if we do at -1. If at -1, if we draw in the triangle, we could count the hash marks and see that the slope would be -2, as we might expect since these are symmetrical. And notice that the derivative is -2 at that point. The other place to look at perhaps is at 0. What is the slope of the tangent line at 0? Well, that's a horizontal line. and we know the slope of any horizontal line is 0, which also is the value of that derivative on the red line. So looking at that, if we count the grid marks, we can actually estimate what the slope would be at those points. We would recognize up here, higher on the graph, if we were to choose something up here, that should have a higher, steeper slope, which the values on the red line are higher up at that point. Over here, we should expect to see larger negative numbers, which is what we see on the derivative here. So the derivative is a way to express the slope of all of the tangent lines on this blue graph. The red line represents the slopes of all of the slopes of the tangent lines on this blue parabola that we have here. So I've shown those calculations here. This is what we were just looking at. At x equals 1, we counted and found out the rise over run was 2. And then we plugged it into the function 2x and found that the actual value would be 2, which is the same. So counted slope of the tangent line and calculated slope of the tangent line are the same thing. I did that also at -2, and we found out the slope would be -4 if we counted. And if I plug it into the derivative, it's -4. And we did a 0. The horizontal line told us the slope of the tangent line was 0. But if we plug it into the derivative 2x, then we found out using f of x equals 2x. Then plug in a 0 for x, we found out again that it's the same thing we get when we count. The point is, if we use the limit definition or other derivative rules, we can find the value of the derivative at a given function by plugging in the x value into that equation of a derivative that we got to find the slope of the tangent line or the instantaneous rate of change at that point.